Okay, so I know in the past, the last video, I promised we get past the Bachman-Howard ordinal, which is this here. But before I do that, I want to address a little bit of an issue we're going to have. We never really plugged in these infinite collapsing ordinals into the fast-growing hierarchy to see what they do. So if I were to give you something like f psi omega to the omega of 3, how would you deal with this? Well, basically the only method we've learned is to translate this into a known ordinal, something we're used to, and then plug that into the fast-growing hierarchy and deconstruct it. But what if I gave you something like f psi of omega to the power of omega to the power of omega, which is defined as the supremum of all of Veblen notation? You'd now have nothing to translate this into, so you'd kind of be stuck. You'd be able to represent this, you'd be able to say it's a very large number, but you wouldn't be able to go any further than this. So it's clear that we need a more robust definition of this. We need a better way of deconstructing these ordinals. And the way we do this is we deconstruct them in terms of other infinite collapsing functions. So to start, let's pick a smaller ordinal. Let's say epsilon 1. Now what is epsilon 1? Well, it's an infinite tower of epsilon naughts. And we could also write it as the fundamental sequence epsilon naught to the epsilon naught, epsilon naught to the epsilon naught, to the epsilon naught. Now let's rewrite this in an infinite collapsing function. Epsilon 1, as we know, is psi of 1. And epsilon naught, as we know, is psi of 0. So we can write psi of 1 is equal to psi of 0 to the power of psi of 0 to the power of psi of 0. Blah, blah, blah. And we can also write this as the fundamental sequence psi of 0 to the psi of 0, so on and so forth. And you can imagine now replacing this 1 with just an a, and we could say in general that e to the a is equal to e to the a minus 1 to the power of e to the a minus 1 in an infinite tower as well. So we can say that psi of a is equal to an infinite tower of psi a minus 1. And we could write an infinite tower similarly as this double up arrow omega. It's just another way of writing an infinite tower here. Okay, so that's kind of cool. We have a way of deconstructing this kind of ordinal in terms of another infinite collapsing function, basically. And a can be a number, it can be an infinite ordinal, but this formula doesn't work for things like psi of capital omega. To deal with capital omega, we need something different. So first of all, let's represent this as an ordinal that we know. So this is analogous to zeta naught. And zeta naught is defined as an infinite nesting of epsilons, or as the fundamental sequence epsilon naught, epsilon, epsilon naught, epsilon, epsilon, epsilon naught, etc., etc., etc. So now let's put this in terms of an infinite collapsing function. So epsilon naught, as we know, is psi of 0. Now for the next element here, how do we get epsilon naught? Well, we get that by plugging in epsilon naught into the psi function, which is this here. So we take psi of 0, which is essentially psi of epsilon naught, which is going to be epsilon naught. To get the next one, we plug this guy here into the psi function as well. So we get psi of 0. Blah, blah, blah. So now we've successfully turned a psi with a capital omega inside into a fundamental sequence in terms of other collapsing functions, basically. So let's keep going with this. What about psi capital omega times 2? Now this one is kind of tricky. First thing we're going to do is write down the fundamental sequence for this. So this is equivalent to zeta 1, which has the fundamental sequence zeta naught plus 1, epsilon, epsilon, zeta naught plus 1, epsilon, 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 zeta naught plus 1, etc., etc. So that's the fundamental sequence we want to match if we want to put this in terms of infinite collapsing functions. So basically, we can think of this as kind of diagonalization of capital omega. So kind of similar to how you would have omega 2. We split that apart into omega plus omega. We'll do the same thing with this guy here. So we'll take psi of omega 2 is equal to psi of omega plus omega. And let's look again at this guy right here and think of what's really going on here. So basically we're starting with psi of 0 as the first element in the fundamental sequence. And to get the second element, we're taking this guy right here and we're replacing him with the first element in the fundamental sequence. And then to get the third one, we're replacing this guy with the second element of the fundamental sequence. And we keep on developing new elements in the fundamental sequence in this way. So let's do the same thing here. We're going to start with psi of 0. Now this might seem a little strange. We're starting with the same element for the fundamental sequence of two different ordinals. But just for elegance of the equation or whatever, this is going to be an important part of it. So just, I know it seems a bit weird, but it just it works out that way. For the second element, what we're going to do is we're going to take this guy right here. So just like if you were diagonalizing this here, you'd diagonalize this guy here. You take this one and replace him with the first element in the fundamental sequence. So we end up having psi capital omega plus psi of 0. Now to get the third element, we replace this guy with the second element of the fundamental sequence. So we rewrite this here, and we get psi capital omega plus this whole thing right here. So psi capital omega plus psi of 0. And before we go any further, let's translate this back into ordinals that we know to see how close we are to this fundamental sequence here. So this right here is epsilon naught, so we'll just write that over here. What's psi of capital omega plus epsilon naught? Well, it's the epsilon naughth epsilon number after zeta naught, which is a bit of a tongue twister. And then to get psi capital omega of that, it turns out to be epsilon zeta naught plus epsilon zeta naught plus epsilon naught. Okay, well this looks a little bit different than the third element we had before. So let's maybe do a little bit of rearranging here. We observe basically that this here we can rewrite as, let's do a little simplification of this basically. Let's take, instead of having this epsilon 1 here, let's take a smaller ordinal. So we'll take zeta naught plus epsilon zeta naught plus 1, and we'll see what properties this has here. Well, epsilon zeta naught plus 1, we can rewrite as an infinite tower of zeta naughts. So we can rewrite this as zeta naught plus zeta naught to the zeta naught to the zeta naught in an infinite tower. Well, we know that zeta naught to the power of an infinite tower of zetas is just equal to an infinite tower of zetas, which can be written as epsilon zeta naught plus 1. So clearly, zeta naught plus an infinite tower is still just equal to an infinite tower, which is equal to this. You can do kind of a, I guess, a squeeze theorem type of thing to prove that. And because this is much, much smaller than this with an epsilon naught at the bottom, this will apply. So we can replace this whole thing here and get epsilon zeta naught plus epsilon naught, basically. So this is our final term here. Now this is still a bit different than our classic definition of the third element of the fundamental sequence, which would be epsilon, 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 zeta naught plus 1. For instance, this element here is a bit bigger, and we have one less epsilon in the thing. But the way we want to think about it is the growth of the function, basically. If we can imagine tacking on additional elements of the fundamental sequence, we'd keep on tacking on epsilons in this nest. So this basically keeps pace with the fundamental sequence that we're used to. It's just not exact. And we're not really worried about things being exact. The fundamental sequence is essentially shifted over just a tad. But when you're dealing with numbers that are very, very, very large, just like in the beginning, it didn't matter whether you built a exponential tower of 2s or 10s, it ended up being almost the same when you reach very, very large numbers. Same kind of thing. If you shift over the fundamental sequence a little bit, it doesn't really matter. And the elegance that we'll get for this way of converting ordinals, it'll be worth it to be a little bit off with fundamental sequences. Okay, so let's move on now. Let's try eta naught, which is psi capital omega squared. Let's break this apart into psi capital omega times capital omega. And once again, we're going to start the fundamental sequence at psi of 0. For the next element, we're going to replace this guy here with the first element of the fundamental sequence. So we're going to get psi capital omega times psi of 0. For the third element, we're going to get psi of capital omega of this guy right here. So replace this with the second element of the fundamental sequence. So we get psi capital omega times psi of 0. And once again, we'll stop to check our work basically. Let's translate this back into an ordinal that we know. And if we deconstruct this, what we find is we get zeta, zeta, epsilon naught. And the classic definition, the third element of the fundamental sequence of eta naught, is zeta of zeta of zeta naught. So once again, a little bit different, but this will also keep pace with this. It's just shifted over a little tiny bit. So we're still all right. Let's move on. Let's try psi omega to the omega. This is already by itself here, so we can keep this as it is. We don't have to break it apart. And we start the fundamental sequence again at psi of 0. The next element, we replace this with the first element. So we end up with psi capital omega to the power of psi to the 0. The third element, we're going to replace this guy with this whole thing right here. So we get psi capital omega to the power of psi capital omega to the power of psi of 0. And this here, if we translate this back to ordinals that we know, we get psi of epsilon naught of 0 of 0. And the classic definition would be psi of 0, basically. So once again, a little bit different, but it keeps pace. So it seems like this method works. And as it turns out, we can do this for any arbitrary power tower of capital omegas. This works all the way. When we get past Bachman-Howard ordinal, we have to make a few variations, but this is a very, very powerful method. And with this, we can evaluate everything up to the Bachman-Howard ordinal. So we'll do a few more examples in the next video.